So in recursion, we break down a problem solution or a big problem into smaller pieces or solutions, right? So maybe this is like one big solution, but in recursion we opt to do this instead. Like we have to break it down into smaller chunks to get to the solution. So that's what we do. And what is recursion? So it's a function that calls itself, and just like a loop, it must have a stopping point, and that stopping point is the base case. And we usually use a conditional structure like if to determine if we reach the base case or not. So how does this look in memory? So we have a memory and the heap's not used. But if a function calls itself, well, actually, anytime we call a function, it needs to be loaded onto the stack. And we showed that with variables, right? We never I never really talked about the function being loaded onto the stack, but the function is loaded onto the stack. And then at that time, whatever memory needs, the stack allocates to that function. So if a function calls itself, say we call it one time, and then it's like, oh, okay, let me call myself, and oh, let me call myself. If we don't have a base case, you see, it keeps on calling itself until we are out of stack memory and our program crashes. So that's why we need a base case, because a function just can't call itself. Like we will run out of memory, and we'll demonstrate that. So let me see here. Open folder. Actually, I used the wrong source code yesterday again. So let me go back to the previous one. This one. Okay, so examples 13. Okay, so 13. And 13. So that's the recursive piece. Okay, write prototype for void function display with one int parameter. For now, we will ignore the int parameter. We'll say void display. So that's the signature for our function, and then we will go to CPP, and all we'll do in here is we'll say hello, and maybe we'll say load stack, and let me put this in the header. I know I will eventually need it in main. Okay, So nothing that we've not seen before, right? So let me see here. What did I do? \n. Okay. So we have this function and it displays hello, and then, well, to be a recursive function, then we have to have it call itself. So notice we have to call it ourselves one time, and we will do that in main. So here we'll say, let me call the display function. And it comes in here, it displays hello, load stack, and then it'll call itself again, and it'll call itself again. And notice we've not provided any base case, or we've not given it an out. So it's just gonna keep on loading onto stack memory until this would occur, until this happens, right? So let's see. Configure. I'm still doing it. Okay, there we go. And let's run it, and then you'll see it displaying. Once it starts running, we'll see it displaying, and then it'll flicker. Like you see like right here, it's like executing. I don't know if y'all can see that well, but it's like flashing, flickering, and then all of a sudden we'll see that it stops. So while it's doing that, it's exhausting stack memory, and eventually our program will crash. Because we're loading function calls to stack, and we're never giving it an out so that it can start unloading from memory. So then we ran out of memory. So I think last time it took around 40 seconds to a minute last night. So and then it finally stopped executing. Yeah. So notice like it just stopped executing. It's kind of like the stack blew up. In Visual Studio, I would see like a dialog saying like stack overflow, meaning like I don't have any room anymore. I've not figured out the error handling, the error displays in Visual Studio Code, mainly because I've not really tried to figure it out, but I will eventually. But notice that it stopped executing. So this case happened. It just ran out of stack memory. So we want to provide it an out, so we'll provide a base case so that we can load the stack maybe 3 times or 4 times, and then eventually just unwind the stack. So what are we saying? Okay, so that's what we want to do with a recursive call. We want to display hello 3 times. And in main, so we'll just do main here. We'll call a display. We will add a parameter to our function, an integer, and we want this to occur on the stack. 1, 2, 3, 4. So we want to call display. I'll just do D with 3, and the base case will be to call yourself until this parameter that we pass is 0. So is 3 0? No. So then call yourself again, but this time with parameter -1. So then we'll say, okay, call yourself with parameter 2. It's still not 0. Call yourself again. Is 2 0? No. Okay, call yourself again with parameter -1. So then we do that, and then one more time is 1 0. No. Okay, call yourself again with parameter 0. All this time it's displaying, this 3 times is displaying hello to screen. Once it gets here, base case, then the functions start returning, meaning they execute and unload from the stack, and then it executes the function that was waiting, which is this one, and then the next one that was waiting, which is that one, and then the next one that was waiting, which is that one, and then finally that one will be unloaded, and then we will have a clean stack again. So notice we won't run into that issue that I purposely caused, right? To show you that we will run out of stack memory eventually if we don't stop the function from calling itself. Okay, so we come back and then we have to add a base case. We go to the header and we said let's add an integer count, and we go to CPP and we have to add that integer count, and we check if count, right, base case, if count equals 0, simply return. And maybe what we'll do here is we'll display base case start unloading the stack. A new line. Okay, oops, semicolon. So if this is not the case, so if it's not 0, first thing we want to do is we do want to display hello to screen. And then we want to call the function again, but this time with count -1. And then eventually we want to show when the function is being unloaded from the stack. Okay, so we have a display of 3. Come in here, count is 3, is it 0? No. Okay, display hello, load stack with count -1, right? So then we call, so this was for main, and this one's the function calling itself, count -1, df2. Count is 2, it's not 0, so then display hello again, and then call yourself with 2 -1. Okay, so notice this step's on hold, because once it goes here, this cannot execute until the function begins executing again. Okay, so 2 -1, 1, so then call display with parameter 1. It's not 0, so then we display hello again, and then we call display with 1 -1, which is 0. This function call here, df0. So count is 0, so if 0 equals 0, yes, then display base case, start unloading the stack, and simply return. And we can do that, even though it's void, we simply return, meaning like exit the function. And it starts returning to df1. Okay, so df1 left off execution here, so then the next step that's executed is unload stack. And then we go to the previous function call, which was df2. Again, that one also left off here when we called it, so then it'll display unload stack again. And then we will call finally df3 again, and we will say unload stack, right? So questions here? Like, I'll run it to show you that that is what's happening, but are there any questions? Now we're changing it here. See, each time we call the function, we do count -1. So originally it's 3, and then we do count -1. So then we do df2, right? So that's how we're changing it right here when we call it. Otherwise, like, if we never change count, then we would be back into the same situation where we don't have a base case formed properly. Okay, so here, run in terminal. Well, before I run it, this one has to be loaded onto the stack from main, right? So load stack. And then after it executes, it's unloaded from the stack. So then we have to say unload stack, just so that we can show the text to match our diagram. Okay. Run in terminal. So load stack, this is from main, and then it calls itself df2, this one, right, df2. Then it calls itself again with df1 right here, calls itself with df0, and that's when the base case is reached. And then we start unloading the stack exactly as many times as it was loaded, right? So 1, 2, 3, 4, and then we have 1, 2, 3, 4 unloads. And that is a simple example just to show us how recursion works, right? All it does is display, but the main purpose of this example is to show us the mechanism of how a recursive function works. Any questions? Question? Mm-hmm. Yeah, I can do that. Okay, so display of 3. So this one is a function call, so it has to be loaded onto the stack. It's this one right here. Okay, so then we go into the function code. Count is 3. It's not 0, so this block is skipped. And then we come here and then we display hello load a stack. Okay, and maybe if we put more message in here so that we can, maybe we do here count -1. Okay, and if we create another variable c, and then before we call the function, we save c. So we say c equals count -1, and then over here we'll after it starts executing itself again, we will display c. Put a space there. Okay, and then we'll run this. But okay, so this was 3, it's not 0. Call yourself again right here. So call yourself again with 3 -1. So that's df2. We have to load that function call onto the stacks. It's right here. All right, it's 2. This is skipped because 2 is not 0. And then we call ourselves again with 2 -1. So df1. We load that one onto the stack. Count is 1. It's still not 0, so we skip this block again. We're displaying each time hello load stack, right? And then we say, okay, I'm going to call display again with a 1 -1, so display of 0. So df0. Okay, so the parameter count is now 0. That's should be the base case. Count 0 is count 0. Yes, okay, display base case, start unloading the stack. And we return, right? So this return unloading, or some call it unwinding the stack. So then it jumps here, and actually we return, and each function was pending execution of this statement, right? So then it's display of 0 would have been waiting here. So then we say, okay, unload stack, right? And then that one's unloaded. That one's unloaded, so then we're now at 1, so df1, right? And that one also left off here, so then we unload that call, And then once that happens, then the stack knows that that function is finished executing, so then it does D2, and then that one also we left off pending execution of this function call, right, with a different parameter obviously, and then we say unload stack, and then we're back where we started with D of 3, and D of 3 is what started the recursive call, but we left execution here, and then this statement executes. And then we can run this code with the new markers I added, so that hopefully that can help us track it a little better. Right, so load stack with 3, right? This was for main, so this is load stack with 3, and then load stack with 2, load stack with 1, and load stack with 0. So that's the base case, and you see that's why we display base case, start unloading the stack. So then the stack is last in, first out, right? So you were the last in, so you're the first out, and then 1, and then 2, and then finally 3, and then the stack is free again, right? So we unloaded the stack, so then there's no function calls anymore after the main display 3 concludes executing, and then we go on to the next statement. We would have an empty stack. Any questions? You'll just have questions about how to set up a recursive. You're not gonna, I mean, you already have the questions, right? So I'm not gonna ask you to write, it's gonna ask you what happens if there's no base case. What are the basic parts of a recursive function? Well, it has to call itself, and then we have to have a base case. I mean, I think there's only like 2 or 3 questions maybe, if you get them. So I mean, that's if you understand that a base case prevents an infinite loop, right, of recursion, and then you run out of memory, then you should be fine. Okay, so that was just to show you, right? So now let's do something meaningful, like solve a problem. So if we recursive factorial. So we know that a factorial, for example, the factorial of 5, we know we have to do 1 times 2 times 3 times 4 times 5, and then we get that answer. So this lends itself to, so we can do this in a loop, no problem. Like we proved that we can solve the factorial with an iterative solution with looping structure, do, for, or while. But we can also solve it recursively if we break this down into smaller pieces. Like if we say, okay, one piece is 1 times 1, right, 1, and then I can do 1 times 2, 2, and then 2 times 3, 6, and then 6 times 4, 24, and then 24 times 5, 120. So if I can do that and break it down into pieces for a recursive call, then that'd be great. So can that be done? Yeah, it can be done. So we come here. So okay, so integer value return function factorial, and we need a number. Okay, so we have this piece of code, and then we can write some code. This you will need for data structures. I've seen their syllabus, and they hit recursion for some of the problems you have to do. So at least you're exposed to it here, and it won't be completely foreign to you when you get to data structures, right? So F to track return value, right? That we're going to return integer. And then integer R recursive function call return value. You'll see what that means. Okay, so base case, if n equals 0, we know that the factorial of 0 is 1, so we return 1. That's the base case. And then we'll do some tracking. We'll say, okay, cout load stack, and we will track the argument n minus 1. So that's a parameter. And we have to track the return value. So we'll say, okay, the return value will be factorial of n minus 1. And we track the, we don't have to do this, but I'm doing it so that when we run the function, we can see everything that's happening on each recursive call. Tracks each, well, I guess I already have it up there, so we don't have to do that anymore. So then here, factorial of n minus 1 means call yourself again, okay? And then we say, okay, if factorial equals number times the return value. And then we say, okay, cout unload stack. So we want to unload the stack, but then we want to track some variables. We want to track n. So we say n is n. And then we want to track the return value, R. And finally, we want to track the value of F. And new line. F and then new line. And finally, we return F, which will be the product of multiplying all those numbers by themselves, by each other, right? So, okay, so how would this work in a diagram? Okay, so we have it there, and then in main, we'll do factorial of 5. So factorial of 5. R for return value, and n will be in each function call, right? So we'll say f of n. So each function call will be the parameter. Okay. Factorial of 5. So from examples, we know that this one has to be loaded onto the stack. I'll just say f of 5, right? So f of 5. N is 5. Is it 0? No. Load stack, display n minus 1. Okay, meaning we will call the factorial with 5 minus 1. So now we will have f of 4. there's no return value yet, because let me make sure I don't. I'm trying to use the mouse. Let me shorten this one. We'll do this. That way we can track the return value once they start returning. So there's no return value yet because we call the function again. So these steps right here are pending execution. That's why we don't have a return value yet, okay? So then call the factorial with f of 4. And it's 4, it's not 0. Display load stack, and then call yourself again with 4 minus 1. Okay, so 4 minus 1 we know is f of 3. And then we go back. It's not 0, so call yourself again with 3 minus 1, so f of 2. Two is not 0, so now call yourself again with 2 minus 1, f of 1. Not 0, so call yourself again with 1 minus 1, so factorial of 0. The base case, n is 0. If 0 equals 0, so n is 0, so return 1. Okay, return 1. And then we're left off there, right? Oops. So we had called, sorry, I'm looking for that. We had called factorial with parameter 1. Or n, right? So, or n. So we come back to the code and we are here. So parameter 1 and times the remainder. Let me use a different color. Multiply them. Okay, 1 times 1. And that's f. So we return f. One. Oops, maybe I should use blue here. I mean red. 1. Okay. And then f of 2 is pending execution. So now the parameter is 2 and the remainder is 1. 2 times 1. 2. And, right? And 2 times 1. 2 will be the next return value according to our code, right? So f is 2 and return it, so 2. Okay. And then we were left with execution f of 3 now. So we're f of 3. So n is 3. So 3 times 2. 3 times 2. 6. So that's the return value. Okay, so then we go back to the next function which was pending, which was f of 4. So 4 times return value, 6. So 6 times 4, 24 is the new return value. 24, right? We did 4 times 6. And then the next return value is 24 and the last function call that's pending was factorial of 5. So 5 times 24, 120. And that's the factorial of 5, right? So that's how we would solve a recursive a factorial with a recursive solution. So questions before I execute the program? Oh, because the factorial of 0 is 1, right? So that's why we return 1. Yeah. Okay, so let me go back to main. So here we say factorial of 5. Okay, and let's run it. Okay, so load the stack with 5, load it with 4, load it with 3, load it with 2, load it with 1, and finally the base case. And then we start the multiplication, right? So 1 times 1, the return value or the factorial, right, is 1. 2 times 1, 2. And 3 times 2, 6. 4 times 6, 24, and then 5 times 24, 120. Finally, right, we unload the last call from the stack, and we have our return value, which we should probably print, right? So we should say int f equals, and then here we should say cout factorial is f. And we have the correct answer, right? Factorial of 5 is 120. And the book examples, they don't like do the local, create local variables like I did. But I do them in hopes that like students can go in there and trace the code, right? Like I'm hoping that would displaying the values in each return function, that you can see what's happening and hopefully get an understanding for how a recursion works. So questions here? Yeah. Yeah, the main, I mean, it's mainly like load the stack, right? Factorial, and then we have unload the stack, and then we display the factorial. So you will use recursive functions in data structures. And I showed you a free function, but you can also have recursive class function calls, right? I mean, after all, a class function is still a function. It just belongs to a class. And you'll use those for, what was that search? Oh, I forgot yesterday and I forgot again today. I have it here, hold on. If I can find it. Well, while I'm looking for that one, another use case is for graphics applications. So when they're displaying a window, then they call the function that displays the window again and again. That way they can keep on refreshing the window, right? So let me see here. I'm pretty sure I can find it quickly. So that's another use case. And in data structures, I'm almost there. Quicksort. So you'll use it in the quicksort. And some professors like ask you to write the quicksort code, and others ask you to analyze the quicksort code. So it depends on who you get, but that's when you'll use recursion. Okay. So any questions on recursion? That's all I wanted to cover on recursion. The next topic will be introduction to algorithm analysis. And this is from chapter 9.6 in the book. So the first sections, 9.1 through 9.5, they talk about some code that I actually need right now. Let me get it. And it's a sequential search, a binary search, and then not a binary, a binary search, and then which is the other one? I have it here. Algorithm example. Linear search, binary search, and bubble sort, right? So, and then we're not gonna write code. Like not even me. I'm just gonna copy and paste some code, and then I'll show you how it applies to the lecture piece, right? So let me go back here, and we have an algorithm, and what is an algorithm, right? So we can say there's steps to solve a problem, like very generic, very layman's definition, right? Like layman's terms, like we don't need to get fancy with that. So researchers, right, since computer science field started, they started analyzing algorithms, and they wanted to be able to categorize algorithms, like search algorithms. They wanted to categorize them, like which one's faster if I use this type of search, or which one's faster if I use a bubble sort, right? And how do we tell programmers, or how do we know which one to use, or sorts, right, for sorts? So one thing that they wanted to do was, well, measure the speed, like measure the speed, right? Like meaning like how many, I don't know, milliseconds or whatever, right? Like how many milliseconds did it take? But that brings up some interesting issues, right? Because who writes the code? An expert, an intermediate guy, meaning somebody who more or less knows how to write code, or a novice. So then that is kind of like, well, I mean, is it really work? I mean, is it really going to work? And then the other piece is hardware. Like somebody might have legacy hardware, right? So we won't say old, right? Like legacy hardware, cutting edge hardware, meaning like the latest and greatest, fastest supercomputer. So then if a novice runs the algorithm in legacy code and an expert runs it in cutting edge technology, like, are we really measuring? Is the speed really meaningful? And the answer is no, right? Because there's too many questions. There's too many variables if we just simply want to measure them with raw speed. So then that's out of the question. So then the second approach, some math geniuses were like, what if we use a mathematical approach to it? for example, a linear search, right? So what is a linear search? If we have 1, 2, 3, 4, 5, 1, 2, 3, 4, 5, 6, right? And we're looking for, I don't know, some number. We're looking for the number 5. Actually, a linear search would be sorted, right? So if we're looking for this guy, then we have to go through every single element in the array. So if there is n values, we have n basic steps, meaning as we have to say, like, is my search value equals to this number? Is my search value equals to this number? Is my search number equals to this number? So that's a basic teams. Why did I put basic teams? I was thinking of work, sorry. They're talking about Microsoft Teams. Basic steps. So we can say that a linear search will be as fast as the elements we have. So here we have 1, 2, 3, 4, 5, 6 elements. So 6 ends, right? But if we have, and then how many basic steps? Well, that's 6. But if we have 10K, then we still have n steps, right? Like it's just 10,000 steps. And what about the speed? Well, the basic steps are the same. Now instead of doing 6, we're doing 10,000. So then we can say that the linear search will grow proportionally to its data size, right? So then they call that measurement O of n, meaning like no matter how many elements we have, we can measure that as with n. And what does n mean? Like with basic steps, right? So if we have 5 basic steps, then it's O of 5. And if it's 500,000 items, then we know it's O of 500,000. We will have to do that step 500,000 times potentially if the item we're looking for is the last one in that element, right? So then they're like, hey, well, that kind of makes sense, right? But what about for other algorithms? And other one, like which one? Like a bubble sort. So a bubble sort, we're not gonna go over the code, right? But in short, a bubble sort if we have some elements, it starts comparing 2 values at a time, and if this one's less than this one, then we swap them. And the same thing here, and the same thing here, and the same thing here. The only problem is we probably have to do that by looping. So this is n, right? By looping through our data set more than this guy, right? So then if we do n, then we can say, oh, that's n times n, or n squared, right? So meaning O of n squared. And hopefully this visual kind of like shows you, right? Like, oh, wait a minute, the linear search like will always have n basic steps equal to the amount of n values. But for the bubble sort, we'll have n squared basic steps because we have to go to the data set to constantly be comparing 2 elements until we have it sorted, right? So that is O of n squared, right? And then we'll graph this so that you can see what we're doing, right? So again, linear search meaning like the speed grows proportionally to the data size. Bubble sort means that as the size grows, then the time it takes to sort the data set will be very, like, it'll go out of control immediately. Like if we have maybe like 20K, we're okay. But if we have like 1 million, then we can see here that we'll, like, the time will just keep on like going out of control. So then bubble sort is good for small data sets. And this one, I guess we can kind of be like, oh, I guess it's okay as long as we don't have 10 million items to search, right? So this one depends, maybe good for also like small to medium data sets, right? And then finally we have the binary sort. And the way the binary sort works is if we have a lot of records and it's sorted, and we are looking for something that starts with A, and say this is the midpoint, then we can discard, we can delete the second half of the elements, because if it's sorted and we're looking for something that starts with A, we're not going to find it over here. So we just eliminate it, right? So the math geniuses were like, well, yeah, like if we use that type of a search, then as the data grows larger, the time it takes to sort them won't. Did I say binary sort? It's search, right? Binary search. Sorry. The time it takes to search for A, it's really not too bad. Even if we're searching for something with Z, it's really not too bad, because we'll eliminate half of the data set. So then if we have 100,000 and the speed is, say, like 10 milliseconds, then 200,000 will only add a few more milliseconds. Like the time will not be out of control. So then this type of algorithm is categorized as O log 2 of n, right? So if we diagram this, so the book talks about big O notation. I won't like get into how they derived this, right? Just go to show that they decided, well, we'll use the mathematical categorizations, right, to categorize our arrays, right? And the book has like one section of algorithm analysis. There's books that are devoted to algorithm analysis, and there's classes that are semester-long courses for this. You don't have to take it at ACC, but only if you transfer like to a university, then it's a junior level course and you'll take it there, right? So if we graph this guy's, we have time, then we can and visually see that our graph will be okay. Let me see here. Sure, I get the graph correct. Okay, so we have our graph here. This is time right here, and then this will be the size, right? So obviously growing. So we'll start with the first one, which was O of n, right? So O of n, the linear search, we can say that it grows proportionally to the size of the data. So that's how we can graph it. The next one I talked about was n squared, right? So O of n squared which was the bubble sort. That one we set as data grows, this time goes out of whack. Like the time increases exponentially. So this one we can draw kind of like this. So as the size grows, then the time is just goes out of control. So this is O of n squared, meaning we have 100,000, it might take 10 milliseconds. We have 200,000, it might take 60 or 100 milliseconds. Like it'll just go out of control, right? And finally, we have bread, and that would be O of log n, 2 of n, right? And this one was the binary search. And for this one, we said, like as size increases, the time increases, but by a little bit, not by a lot. So we can graph that one kind of like this, and this one will be O log 2 of n. And then the last one is a bonus. We have the basic step, and a basic step is always constant, like meaning comparing two numbers is always going to take the same amount of time, so it's constant, right? Like that would be an example for that one. I meant to draw the line straight, but it got crooked. Okay, so we can show this graph is true. We have what? Yeah, we have time. I just have to get some code in here. So we'll go here. No, here. Is this one empty? Not empty. Compare. Is this one empty? Okay, this one's empty, so I can paste some code in there. And this is the header. Okay, let me get some code and paste it. It'll take me too long to type the code. Okay, so that's why I'm just pasting it. I'll briefly explain it. So we'll have a function populate array, and then we'll have a function for a linear search, and we'll have a function for binary search, and then we'll finally have a function for bubble sort. And that's the header. Let's get the CPP code. And paste it in here. Okay. And then finally, we need a main. Not that one. This one. Okay. So main. Okay, and arrays access. Shouldn't be any errors. Yeah, okay. I was just catching up. Okay, so we go to main, and what we'll do is start out with the linear search, right? So what do we have here? We have a stopwatch, right? So we start the clock, and then we start it. Not start it. We get the current time, and then we get the current time, and then we do some math just to see how many milliseconds it took to do something, right? So let's start by calling the linear search function with a list of how many. Well, we'll start maybe with 100,000 records, right? So 100,000 records, create a new list of 100,000 items on the heap, populate the list, and then call the function, right? And then we'll see how many milliseconds we get. Okay, let me look at this guy. Randomize false, right? If it's a linear search, then we want them to be in order, so don't randomize. Okay. And then we can execute it. Array access run. Okay, 88 milliseconds. So then let's say one thing I was noticing was that the time was not very accurate. So that's why they went with categorizations, right, of algorithms. But let's see what happens here. So 200,000. You see, so 3 milliseconds. So that didn't make sense. And I was trying to figure out what was going on. And then actually -5. We're not looking for -5. We got to find the number, right? So let's say, well, -5, I know why, because I want to search for something that's not in there. And that's what I was running into an issue with. Like the stopwatch was returning inconsistent results. This looks better, right? 172 milliseconds, and I couldn't figure out why it was doing that. Let's go with 500,000. But that proves the point, right? That it's better to rate them mathematically and not. Yeah. So you see that this start making more sense. So we were at 200,000, and then we increased to 500,000, and the time is increasing almost proportionally to the size of the data set for the linear search. So that one should be okay. That, yeah, you know, our graph, at least more or less with those 3 examples, proves that this one right here, like as we add more data, the time, it's growing, but it's not growing out of control, and it's not growing a little bit, right? So let's try this one, and that's for the binary search, because that's the next one here. So for that one, we do have to sort them. So randomize, actually, so randomize means not sort, so we want false so that they can be sorted. And then we will start with 100,000, and we run it. So 25 milliseconds for 100,000, and then we say, okay, let's go with 200,000, and we run it. So 214 milliseconds, which doesn't hold true for what we said, right? Like, shouldn't increment by that much. Let's run it one more time. 199, well, maybe it does, but let's try 300,000, right? Shouldn't, it grew by how many? Like almost 9 times, right? So let's see 300,000. 207, right? So 199, 214, 207. Let's run it again just to see what kind of time it takes here. 19, that one's out of whack. Let's run it again. 258, and one more time. 220. So we went from 100 to 200. We saw it increased like 9 times, but then when we went from 200 to 300, it was okay. So maybe now let's, okay, I wanted to try 10,000, 100,000, 200,000. Okay. So we can confidently say that, yeah, that one is following this pattern, right? I mean, we're adding more elements, and it's still, the time grows, but it doesn't grow like, sometimes it even stays almost the same, right? Which holds true that, yeah, this algorithm is matching the graph, right? So finally, we'll do the bubble sort. And this, no, we start here. Start the clock, execute the function, and stop here. So it's measuring this code here, not the program running, right? And we display the time, right? Yeah. Okay, so we have bubble sort, and we'll start with 10,000, and we run it. So 38 milliseconds for, let's run it again, right? Because That's one thing I was noticing, that the number, sometimes the milliseconds were kind of, well, this one seems to be consistent. Okay, then with 100,000. Okay, so let's try 100,000 records. So it increased, what, 3 times? Let me run it again just to make sure. 3 times. See, so that's one thing I was noticing, that the results were not very consistent with what I was expecting. 5 milliseconds, that doesn't seem right. And let me run it 1 millisecond. And let me run it again. 285, so not very consistent results. Let's see with 200,000. Running terminal. 293. Running terminal. 101. So maybe I need to add more records. 51. Let me add to 500,000. See what happens. Running terminal. 201. 42. Yeah. So this is. I don't know why this is. So 225. Let's try 1 million, right? 1, 2, 3, 4, 5, 6. Am I calling bubble sort? Yeah, I am calling bubble sort. Okay, so let's run it. $163. It's even faster. So there is. That's not what I'm expecting. Okay, let me go back to 10,000. 100, 1 million. Well, 2 out of 3 and bad. Let me look at the code real quick, because that's not what I was expecting. So linear search, binary search, bubble sort, swapped equals false, swapped equals true. List size. Okay, let me see how I'm calling it. The list and the size. Yeah, so I'll run it again. So just so that we are on the same page, we were expecting this to take a lot longer, right? Because according to the graph, like the time should grow like by a lot, and from what we're seeing here, that's not the case. So even if we try with like something like 1,000, so 50 milliseconds, and then 10,000. So that goes to show, right? Like that's why they opted for the mathematical categorization of algorithms, right? So you see, like, but 50, 38. Well, I think my computer is that fast, right, to not make a difference. And then 100,000. Running terminal. 195. Finally, 1 million. Yeah, 142. So this one is not this is not what I expected. Okay, let me see. For each radical, if I plus 1, 10, swap. Yeah, so that looks okay while swapped. Yeah, anyways, I'm not gonna worry about it, right? So take my word, right? Like the bubble sort should like grow exponentially, right? Unless I made a mistake in the code, but in reviewing it, I didn't see anything wrong with it. So you'll get maybe like a chapter of this in data structures. So I always want to make sure that students are exposed to this so that they can understand that it's just not programming, right? They're going to teach a theory about computer science and algorithms. So any questions? Let me make sure I pause it.